6.3 Properties of Trigonometric Functions. So I introduced trigonometric functions in 6.2, sorta. I didn't spend a lot of time on some of the more theoretical aspects of it. But we learned that the sine of theta is equal to y. So that's a function that depends on theta. Now theta can be a rotation. This is how I introduced it. But if you keep in mind that radians and degree and rotations are the same and that radians refer to lengths, then hopefully you can sort of see how that ends up being meaning then that you can just plug in values. You can plug in lengths for this. That means that you can plug in any values for that. Okay? Well, if you can plug in any value for the sine of theta, then that means the domain of the function is all real numbers. Okay, you can plug in positive rotations or positive arc lengths, and then negative if you go the other direction. And the same thing is true for cosine. So if we consider the cosine of theta to always be the x coordinate, then if theta again could take on any value in terms of what you're allowed to plug in. Now the range is the outcome. Now if you look at the x's and y's that we get on this coordinate grid, and if we are looking at this and realizing that that's a unit circle, then I think you should be able to figure out, wow, can't talk and write at the same time apparently, that's 0, 1, sorry, that's a negative 1, 0, and here is 0, negative 1. So then you can sort of see what the largest x value is that you could possibly get, which is 1. We never get anything beyond 1, and then we go for the x's, we actually go backwards. The x's get smaller and smaller and smaller until we're at 0. And then we go all the way out to a negative 1, but that's the biggest negative x value you can get as well. Well, those are outcomes, right? These are now the outcomes. The x value here is the outcome of the function. Well, that means that the range for the cosine is from a negative 1 to 1. And the same thing is true for the sine. So the domain and range for the cosine and the sine are all real numbers for domain, and the range from negative 1 to 1. Well, the tangent of theta is defined as y over x, right? We did that a while back. Well, x can't equal 0. So we have a couple of spots, like here and here, where my x values end up being 0. Well, what rotations do I need to get to there? Well, if you start here, the rotation that you need to get from here all the way over there, that's a 90-degree rotation, but we're basing these on radians, so we have to write this in pi over 2. So theta can't be pi over 2. And the next time that it's 0 is if you go 180 degrees further. So that's plus pi, right? So here's pi over 2. So if you add another pi to that, then the next one would be at 3 pi over 2. So you cannot be worth 3 pi over 2 either. Or theta can't be 3 pi over 2. And then it repeats, because if you add another pi after that, you're back at pi over 2, but now pi over 2 from 3 pi over 2, 3 pi over 2 plus pi is 5 pi over 2. And you can sort of see that this just ends up repeating. So usually one way you can write that Dennis, you can say that theta can be all real numbers, except theta cannot be equal to pi over 2, 3 pi over 2, 5 pi over 2, and then just repeat the pattern. Okay. Range for tangent is a little different than what you get over here. So keep in mind that the range is the outcome of y over x. Now sometimes y is really small, right? So when y is small, 0, x is really big in terms of the biggest values that you get, and 0 divided by 1 is 0. So tangents can be 0. Okay. Can there be negatives? Well, let's see, if I'm over here, so if I have an xy value over here, if that's the x and that's the y, and the x is negative and the y is positive, so if I do the tangent of theta over here, sorry it's all backwards, but then I get a negative here and I get a positive there, so you can get negatives out of tangents as well. Okay, where it gets interesting, or where you need to really pay attention, is if you're really close over here. So let's look at this one a little bit closer. So if I'm at the tangent of theta and it's y over x, okay, and if you're really close, wow, let's try to do that with a straight line. So if I'm really close, so say I'm over here, right? then I have a tiny little x value over here. So like a tiny number would be 0.01. And I actually have a pretty big number over here. It's not quite 1, but it's, it's almost there. So it's 0.99 maybe, something like this. So can you sort of see that when you divide this out, you're actually going to get a large number? And the smaller this number gets, the bigger the value you will get that comes out of the fraction. Well, that means that it actually ends up going to infinity. So the tangent approaches infinity over here, okay, and it approaches negative infinity over here. So the range for the tangent is then its all real numbers. It goes from a negative to a positive infinity. Okay? Well, then we have the little brothers and sisters. So the sine is related to the cosecant, right? So the cosecant is 1 over y. Okay? Well, 1 over y, you cannot have a y that equals 0. So now I have to do the same story that I did over here. So now I have to find the thetas for which y is 0. Well, the first one's right here. So that's a rotation of 0 radians, or 0 degrees. Okay, the next time that the y is 0 is if you rotate all the way from here, if you rotate all the way over here. Well, that's pi, right? That's pi, so that's pi. And then hopefully you can see that it repeats, so then, it happens again at 2 pi, etc., etc. So the domain for the cosecant are those rotations other than, so it's all of the rotations other than these. You cannot have a theta that equals to 0, to pi, or to 2 pi, etc. Well, these are just multiples of pi. Okay? The range then would be sort of the little split of this. So the range would be, well, the smallest, not smart, how do I say that? So the range is going to be the y values that, I don't want to say y values, sorry, because that confuses you with this one. Okay, so the range is going to be less than a negative 1, so the smallest negative number you can get is a negative 1, and greater than 1. Okay, it's basically, let's see, it's cosecants related to this one. So the way that I think of this is since they're, sort of flipped, you take this thing and you split it. So instead of from a negative 1 going in, you go from a negative 1, you go out this way. So that's the smallest negative value. And it has to start at 1, and then it goes out to infinity that way. Okay, so then let's look at the secant. So the secant of theta is 1 over x. So that means that x can't equal 0. Well, we already did that one. Okay, so I can do this one a little bit quicker. So it's all real numbers, except theta can't be, x's are 0 when theta is pi over 2, 3 pi over 2, and 5 pi over 2. And then the pattern repeats. We get the same range over here. And then the last one's the cotangent, and the cotangent is flipped with that one. And so if the cotangent flips that one, you get x over y. Well, x over y gets you this one again. So the cotangent, you can plug in any value you want into the cotangent, except you cannot plug in thetas that give you a y value of 0. So no 0 no 0 rotation, no pi, no 2 pi, no multiples, and then I can do the same story for the domain. For the range as the tangent. So, but now it occurs, like the infinities are going to occur here, and the negative infinities are going to occur here. Okay, and then the zeros would occur here and at 90. Okay, all of that is summarized in this table over here. I honestly don't have this memorized. Well, I have some of it memorized. I have the ranges memorized more or less, but then over here I have to think about this a little bit. Okay. So I honestly do this based on the definitions that I just showed you over here, and with that I mean these definitions. So when you ask me about the tangent, I think y over x, when do I have x values that are 0? Well, x values are 0 here and here, so now I know I'm at pi over 2, 3 pi over 2, 5 pi over 2, etc. Okay. The other thing that you need to, hopefully you found out by now, one of the other things is that, based on the quadrants, the sines, the cosines, the secants, the tangents, and the cotangents, they are positives and negatives. Okay? So if you keep in mind that the sine deals with the y, then you know that in quadrant 1, the y value is positive, in quadrant 2, it's positive, but then in 3 and 4, it's negative. And since the cosecant is just this one flipped, the positive number flipped is still positive, and the negative is still negative. So, and these two are also related in a way. So the cosine's positive, Okay, that relates to the x values. So in quadrant 1, the cosine or the x is positive, and in quadrant 4. If you're wondering about the quadrants, keep in mind that quadrant 1 is here, so x is positive in quadrant 1, but also in quadrant 4. And then the same with the secant. Then the tangent and the cotangent, well, the tangent's the division of these two, right? Or not these two, the tangent is the division of y over x. So it's the division of sine and cosine. So it's only positive if the signs are the same. So if you get a positive and divide it by a positive, then you get a positive number. So that occurs, both the sine and the cosine are positive in 1, so the tangent is positive in 1. Here, the sine is positive because I get positive y's, but I have negative x's. So tangent here will be negative. But here you get a negative x, right? And if you go down, you get a negative y, and two negatives divide out to a positive. So here the tangent is positive again. Okay, and then here it would be negative again because one of them is positive, one of them is negative. The cotangent's just flipped, so it has the same values that way, or the same signs. Another definition, periodic functions. So a function is periodic if you can find an interval in which all the values occur, and then after that interval all the values repeat. And then after that they repeat, and they repeat, and they repeat. Well, for us that just depends on rotations. So the sine, for example, starts here, and after you go through one full rotation of 360 degrees, you've gone through all the values. Because right here, the sine is worth 0. It takes up to here to get to 1, right? Now we're at 1. Then you got to rotate this 90 degrees to get back to 0. And then now you get your negative 1. Right? So that's the largest negative value you can get. And then it takes another 90 degrees to get back to 0, and then it repeats. And that means that the cosecant also repeats after 2 pi. I can do the same story for the cosine, except the cosine starts backwards. The cosine starts with the largest possible value, and then after 90 degrees it's the smallest value that you can have that's not negative. And then it takes a while to get back to 1. And then it becomes immediately negative, and then it takes a while to get back to 0, and then it takes a while to get back to 1. So these are periodic over one rotation, so we then say that the period is 2 pi. The tangent and cotangent actually only have a period of pi. Okay, if you go, and the tangent actually goes from here to here. So we'll look at that a little bit more in detail in some of these other sections, but the tangent here is a negative 1, then it goes to 0, and then it goes to a positive 1, and it does that in the rotation of pi radians. So the period for the tangent and then also the cotangent, that would be pi. So that's something that you probably should have memorized. Okay, finding exact values using periodic properties. Okay, so the sine of 390 degrees is the same as the sine of 360 plus 30 degrees, because that's one full rotation. So if I just knew what the sine of 30 degrees was, I would be in great shape. And I should know what the sine of 30 is. So the sine of 30 is, now in case you are not sure, in my mind, sometimes I still do this on paper, 30 degrees looks like this, right? So the sine is 1 over 2. It's a half. So the tangent of 19 pi over 3, or over 4, sorry. So I can split that in 16 pi over 4, that's the largest unit, the whole number I can take out because the period is pi, and 16 pi over 4 is just 4 pi, so you can ignore that. So that's the same as the tangent of 3 pi over 4. Well, the tangent of 3 pi over 4, if you think of your unit circle, pi over 4 is 45, so this is 1 pi over 4, 2 pi over 4, so 3 pi over 4 would be over here. So now we're looking for the tangent based on this value, so we have a negative x and a positive y. It's a 45-degree angle, so it's a negative 1. Or you can have it memorized. So the cosine of 7 pi, so I can take a factor of 2 pi out of there. So the cosine of 7 pi is 6 pi plus pi. So this one just returns it back to its starting point. And what that means, I'll show that once, is that if you rotate 2 pi, you're here, 4 pi, you're here, 6 pi, you're here, and then you rotate pi degrees. So it's just the same as the cosine of pi. And the cosine of pi is the x value, and then the x value at this location is a negative 1. So it's a negative 1. Okay, so that's how you can use some of those properties. Then we have some fundamental identities. We've already seen most of the ones here. We've already seen that you have the tangent sine over cosine, and this one's just flipped, and the cosecant is 1 over sine. Keep in mind that I've been using it this way more, I think. Okay, so if this is true, then this is true as well. So you can flip all these as well. I did want to show this one over here, and we will prove some more of these down the line, but the sine squared plus cosine squared, that's one of these fundamental properties that you really ought to be able to prove. And so I'm going to prove it rather quickly over here. Okay, so we'll just try to use this to draw sort of a unit circle. So we said in the unit circle, we said that the x value is the cosine, right? So that's the cosine of theta, and the sine of theta is the y value. And if this is a right triangle, then if this x is cosine, then x squared plus y squared has to equal this one, and it's the unit circle, right? So there's the equation of the unit circle. I'll just plug it in then. The x is the cosine, so the cosine of theta squared, which is written with a square here so that you don't think you have to square the value here. It's actually the cosine's value that you're squaring. And the sine squared of theta equals 1. So there's that identity. It's pretty easy to prove. Okay? Okay, why did we need it? Well, we actually need it right here, because 1 over the cosecant squared is the sine squared. So that's the sine squared of 35, and then the sine squared of 35 and the cosine squared of 35 equals 1, based on this identity here. These identities just come from dividing, so keep in mind that the tangent is sine over cosine, right? So if I take sine squared and divide it by cosine squared, I get the tangent squared, and cosine squared divided by itself is 1, and 1 over the cosine squared is the secant squared, right? Because they're related this way. So that's how the tangent squared plus 1 equals secant squared comes out. Maybe you can figure out now how to get this one over here. Okay, cosine over sine is actually, sorry, I was going to write a tangent because I'm sort of stuck on the tangent, but the cosine over sine is actually cotangent, right? So that's the cotangent of pi over 3 minus the cotangent of pi over 3. Well, something minus itself is 0. Okay, next part. Okay, so this is to help you with some of the homework problems. So given the sine value here and the cosine value, find the value of each of the 4 remaining trigonometric functions of theta. Okay, so graphically it means this. So the sine of an angle is opposite over hypotenuse, right? So if the sine is the square root of 10 over 10, and I draw a little triangle for that, then this must be the square root of 10, and this must be 10, because that's opposite, that's the hypotenuse. That's adjacent over hypotenuse, so that means that this is 3 times the square root of 10, and we already have the 10 there from the sine, because we're in the same triangle, so the hypotenuse should be the same. Okay, so there's your angle, there's the triangle. What else did I want? So they said find the other 4, right? So the tangent is the square root of 10 divided by 3 square root of 10. So those cancel, that's just 1 over 3. Okay? The cosecant of theta, the cosecant is related to the sine, so it's going to be the hypotenuse divided by the opposite sine, right? So that's 10 divided by the square root of 10. Usually we clean that up, so if you multiply by the square root of 10 at the top and the bottom, you just end up with the square root of 10 over here as an answer. The secant of an angle is the hypotenuse divided by the adjacent side, because it's related to the cosine. So the hypotenuse again is 10, but this one is 3 square root of 10. So if you multiply that one out, we should get square root of 10 over 3, right? What I mean is if you put a square root of 10 over here, and square root of 10 over here, so if we rationalize this, what I should have said. So we get the square root of 10 over 3, and then the cotangent of the angle is adjacent over opposite. That's 3 square root of 10 divided by square root of 10, so that cancels, so that's 3. Okay, so that would be to do it graphically, and that's Really up to you how you do this. You have to be able to do both. Sometimes I'll tell you have to do graphically, sometimes identities, and sometimes you get to pick. So through identities, you would be able to say that the tangent is the sine divided by the cosine. So that would be the square root of 10 over 10 divided by the cosine. So we're just going to flip that one. So that's 10, 3 square root of 10. And I better get the same answer, right? So those cancel, that cancels. So that's 1 over 3. So 1 for 1 right now. That's what we needed. So the cosecant, next. The cosecant would be 1 over the sine flipped. Cosecant is related to the sine somehow. So flip this one. So that's 10 divided by the square root of 10, multiplied by the square root of 10. So that would be the square root of 10. Secant. So the secant is 1 over the cosine. So I'm going to take the cosine and flip it. So that's 10 divided by 3 square root of 10. And multiplying that one out, or rationalizing, would have given us the square root of 10 over 3. So far it's working. And then the cotangent is just the cosine divided by the sine. If I do the cosine divided by the sine, I get 3 square root of 10 divided by 10. There's the cosine. Flip the second one, because multiplying by the fraction is flipping by the reciprocal. And we get a whole bunch of cancellations again. So we got 3 again. Okay? Based on identities. We'll do that one more time. So the problem can be given this way as well. So given that the tangent of theta is 1 over 3 and that the sine is larger than 0. So now you have to use some of the other properties that I showed you a little bit over here. And so keep in mind that based on the quadrants, we know certain things. So for example, in quadrant 1, everything's positive. Quadrant 2, the sine's positive, and that means that the cosecant's positive, and then the tangent, cotangent, cosine, and secant would be negatives. Here the tangent's positive. That means that the other stuff has to be negative, other than the cotangent, because it's related. And here the cosine is positive, so the sine and the tangent and their reciprocals are negative. Okay, so if we know that the tangent's positive, we know we're in either quadrant, so the tangent was positive here, and the tangent was positive here. So we're in either quadrant 1 or in quadrant 3. If they also tell me that the sine is larger than 0, then I know I'm in quadrant 1. So this is a quadrant 1 angle. Okay, so graphically it looks like this. The tangent of theta is 1 over 3. The tangent is opposite 1 over adjacent, so that's 3. Okay, don't think that this is the square root of 2. It looks like it, but 3 squared is 9 plus 1 is 10, so this is the square root of 10. So we're not in the unit circle here. Okay, so there's the angle. Now I drew it in the right quadrant, and that means that I can find all the other values based on this. So the cosine is 3 over the square root of 10. The sine of theta is 1 over the square root of 10. The cotangent of theta is 3 over 1, which is 3. And then the cosine is somehow thinking secant, and I'm still writing cosecant. So the secant's just flipping that one, the square root of 10 over 3. And the sine and the cosecant are related, so that's the square root of 10 divided by 1, which is just the square root of 10. So there we go. So those are the values. If you do this based on quadrants or identities, you still have to keep in mind the whole quadrant 1 thing. So we're in quadrant 1 where everything is positive. And you'll see here in a second why that is. Okay, so if the tangent of theta is 1 over 3, okay, then one of the identities says that the cotangent is just this one flipped. So that's 1 over 3 becomes 3 over 1, which is just 3. Good. Okay, here's another identity then that you should probably use. The tangent of theta plus 1 is equal to the secant of theta. So somehow I got to get to a sine or a cosine, and I can't get to the sine or the cosine just by looking at tangents and cotangents. So here's a connection between the tangent and the secant in its turn is related to the cosine, right? Because that's 1 over the cosine if I knew what the secant was, right? Okay, so if I can find this, I can find the cosine, and then that will lead me to the sine. So I'm going to square 1 over 3. I'm going to add 1 to that. And that's equal to the secant squared. So 1 over 3 is 1 over 9 if you square it. So like this, 9 over 9. So that's the secant squared of theta. So that means that the secant of theta is the square root of 1 plus 9 is 10. So it's the square root of 10 divided by the square root of 9, which is 3. Now here's where the quadrant 1 positive comes in. Because you're in quadrant 1, you know that this is only the positive answer. Usually when we take a square root, right, if I said x squared is 4, hopefully you're thinking, well, x is either plus or minus 2. Because we took the square root of 4 on our own, so you need a plus or minus. So initially, you know, this should be a plus or minus. But because you're in quadrant 1 where everything is positive, you know you actually need the positive version here. Okay? So it's a positive square root of 10 over 3. Okay. Once you know that, for the cosine then you can just flip it. So that becomes 3 divided by the square root of 10. Notice again that I'm not rationalizing all the time, because it's just more time that you would have to spend on it. Okay, so once you have the cosine, you can square that, and then if you add, or if you use this identity, you can find what the sine squared is. So cosine squared 3 divided by the square root of 10 squared is 9 over 10, right? Plus the sine squared of theta is equal to 1. So the sine squared of theta is 1 is 10 over 10, right? So that's 1 over 10. So then the sine of theta is the square root of 1 is 1. Well, square root of 1 is 1 divided by the square root of 10. And again, I need the positive because I'm in quadrant 1. Okay? We're almost done. Next set of properties you need to be familiar with are called the even and odd properties. So I'm not really good at these. I sort of forget about these sometimes. But the sine and the cosecant are an odd function. I'll show you here in a minute why. The cosine and the secant are even functions, and the tangent and the cotangent are odd functions. Okay. So let's look at the cosine first. So the cosine is the x, right? So if you go theta in this way, you're at x. If you go theta in that direction, the negative theta, you're still at x. So that means that the cosine of theta gives you x, but so does the cosine of a negative theta give you x. And that's the definition of an even function. This one's the easiest for me to remember. Keep in mind that if you look at y equals x squared, right, that, did I do that right? Nope. Yes, that should be an even function. Yeah, sorry, got sidetracked for a second. That means that if you plug in x is 2, you get 4, right? That's the outcome, but if you plug in x is a negative 2, you still get 4. So we said that y equals x squared was an even function. Okay? And that's sort of how I have this in my mind. I connect even with y squared, and that helps me here. Okay, odd functions then would be the opposite. So if I go in theta and I end up at y, so if the sine of theta is the y value, if I do that same rotation in the negative direction, I end up over here, and then I'm in a negative y value. So you can see that they're odd. Okay? See if you can figure out why the tangent then and the cotangents are odd. Alright. Find the exact value of. So the cosine of a negative 60 is the same as the cosine of 60. So I'm using the even and odd properties here. And the cosine of 60 is, let's see. So I'm doing this in my mind. So that's 1, that's 2, that's the square root of 3. So it's 1 over 2. That's a half. Okay? The sine of a negative 390 is the sine of a negative 360 plus a negative 30 degrees. Take that one out. So I'm looking for the sine of a negative 30 degrees, which is the same as the opposite of the sine of 30 degrees. And the sine of 30 degrees happens to be a half as well, so this one is a negative half. And then finally, the tangent of a negative 17 pi over 3. Let's see, we can take out as many of these as we can, right? So let's see, the nearest one we're at, we can take out as a negative 15 pi over 3. That's 5 pi exactly. Plus a negative 2 pi over 3. So that's actually the tangent. Ignore that from the properties that we saw earlier, the period of the tangent being pi. So what's the tangent of a negative 2 pi over 3? Well, the negative 2 pi over 3, so did I do that right? Pi over 3, yes. Pi over 3 is 60 degrees, right? So you are 2 of those, so you're not here, you're here. So if that's 60, yes, then this is 1, that's the square root of 3, and that's 2, this being a negative. So the tangent of a negative 2 pi over 3 is going to be the square root of 3 over a negative 1, which is a negative square root of 3. Okay, and I believe that's it. Thank you.